Each kind of LAN or WAN has its own addressing scheme. Computers connected to an Ethernet LAN have unique 48-bit hardware MAC addresses. Wide area networks have their own addressing schemes depending on the technology used. For example, ATM addresses. So, if we build a network based on several different networks sending data across the mixed network, how do we manage various addressing schemes? The simple and elegant solution is to create a common addressing scheme for all nodes, regardless of the network technology. Give every network a unique ID number, and every node within each network another unique ID number. This way, a virtual addressing scheme, on top of the physical hardware-oriented addressing scheme, is created. This is what IP, the Internet Protocol, does. It provides applications with a virtual addressing scheme for the networks and the nodes, IP addresses, and a standardized way of packaging data between all the nodes. For the application developers, it's easier to create an application for one common protocol with one common addressing scheme than to adopt the application for all types of existing and future network protocols. The IP networking made it possible for an enterprise to connect all their hosts and networks into one virtual network. This is called internetworking. This is where the Internet, a global network created with this technology, got its name. A host is a term for the devices that, regardless of function, are connected to the Internet and have an IP address. The IP address consists of two parts. One part is a unique number of the network, and the other part is the unique identifier of the host. A host may have several interfaces, each with a separate IP address. The IP address is also called the IP number. Between networks, we have a device, an IP router, that knows the addresses of the networks. It is connected to and waits to send data to the nodes on those networks. Every machine on the Internet has a unique identifying number, called an IP address. Presently, there are two versions of the IP addresses in use. The first IP version 4 is widely used, and the new one, IP version 6, is appearing on the network more frequently each day. Let us begin with IPv4 addresses. IP addresses actually consist of two different parts of data: the network identification and the identification of a specific host in that network. In IP version 4, the IP address consists of 32 bits, which we divide into 4 groups, consisting of decimal numbers with dots between them to make them readable and easier to remember. The 4 groups of numbers in an IPv4 address are called octets, because each of them has 8 positions when viewed in binary form. If you add all the positions together, you get 32, which is why IPv4 addresses are considered 32-bit numbers. Since each of the 8 positions can have 2 different states, 1 or 0, the total number of possible combinations per octet is 2 raised to the power 8, or 256. So, each octet can contain any value between 0 and 255. Combine the 4 octets, and we get 232, or almost 4 billion possible unique values. The octets serve a purpose other than simply separating the numbers. They are used to create classes of IP addresses that can be assigned to a particular business, government, or other entity based on size and need. The octets are split into 2 sections: network and host. The network section always contains the first octet. It is used to identify the network that a computer belongs to. Host, sometimes referred to as node, identifies the actual computer on the network. The host section always contains the last octet. In IPv4, there are 5 IP address classes plus certain special addresses. Class A IP addresses are for very large networks, such as a major international company might have. IP addresses with a first octet from 1 to 126 are part of this class. The other 3 octets are used to identify each host. This means that there are 126 Class A networks, each with almost 16 million possible hosts for a total of almost 2 billion unique IP addresses. Class A networks account for half of the total available IP addresses. In Class A networks, the high-order bit value, the very first binary number, in the first octet is always 0. Class B IP addresses are used for medium-sized networks. A good example is a large college campus. IP addresses with the first octet from 128 to 191 are part of this class. Class B addresses also include the second octet as part of the net identifier. The other two octets are used to identify each host. This means that there are almost 16,000 Class B networks, each with 65,000 possible hosts for a total of more than 1 billion unique IP addresses. Class B networks make up a quarter of the total available IP addresses. Class B networks have a first bit value of 1 and a second bit value of 0 in the first octet. Class C IP addresses are commonly used for small to mid-sized businesses. IP addresses with the first octet from 192 to 223 are part of this class. Class C addresses also include the second and third octets as part of the net identifier. The last octet is used to identify each host. This means that there are more than 2 million Class C networks, each with 254 possible hosts, for a total of 5 billion unique IP addresses. Class C networks make up an eighth of the total available IP addresses. Class C networks have a first bit value of 1, second bit value of 1, and a third bit value of 0 in the first octet. Class D IP addresses are used for multicasts. Class D is slightly different from the first three classes. It has a first bit value of 1, second bit value of 1, third bit value of 1, and fourth bit value of 0. The other 28 bits are used to identify the group of computers the multicast message is intended for. Class D accounts for 1/16, over 2 billion, of the available IP addresses. Class E IP addresses are used for experimental purposes only. Like Class D, it is different from the first three classes. It has a first bit value of 1, second bit value of 1, third bit value of 1, and fourth bit value of 1. The other 28 bits are used to identify the group of computers the multicast message is intended for. Class E accounts for 1/16, over 2 billion, of the available IP addresses. Apart from the traditional IP addresses, there are some addresses reserved for special and private use. IPv4 host addresses consist of two parts. The first part is a network number, and the second is a host number. The network administrator decides how many bits are used for each part of the internal network, and the Internet Service Provider decides this for the external network. For each IP network, there is a subnet definition, usually called the subnet mask, telling how many bits belong to the network ID. A /16 network uses 16 bits for each part. A /24 network uses 24 bits for the network ID and 8 bits for the host ID. Note that the border between the network and host parts of an IP address doesn't need to be aligned with 8-bit groups. The subnet mask can just as well be 18 bits long. To illustrate this, we represent the IP address in the binary form. In this example, the network part is 18 bits long, whereas the host part consists of 14 bits. 14 bits give approximately 16,000 addresses. The advantage of this solution is that Internet service providers can allocate IP addresses that corresponds better to the size of the customer network. The subnet mask looks like an IP address and usually reads 255.255.255.0. This tells the router that all messages with a sender and receiver having an address sharing the first three groups of numbers are on the same network and shouldn't be sent out to another network. Here's an example. The computer at address 15.57.31.40 sends a request to the computer at 15.57.31.52. The router, which sees all the packets, matches the first three groups in the address of both sender and receiver, 15.57.31, and keeps the packet on the local network. Subnetting blocks out a portion of the IP address to distinguish the network ID from the host ID. The subnet mask specifies whether the destination's host IP address is located on a local network or on a remote network. The source IP address is ANDed with its subnet mask. The destination's IP address is also ANDed with the same subnet mask. If the result of both ANDing operations match, the destination is local to the source. That is, it is on the same subnet. In IP version 6, the IP address is extended to 128 bits, giving us an astronomical amount of possible addresses. Using hexadecimal notation, the address is written in 8 groups, separated by colons. If one or several consecutive groups consist of zeros, only they can be omitted and replaced by 2 colons. IPv6 not only provides a larger address space, but also makes it possible to assign addresses in an all-rational way from the start, than was the case in IPv4. IP addresses actually consist of 2 different parts of data, the network identification and the identification of a specific host in that network. The IPv6 makes address configuration much easier than IPv4. The IPv6 creates addresses based on the hardware interface address. For the Ethernet, IPv6 uses the 48-bit MAC address in a special encapsulation called EUI64, which results in a standardized 64-bit hardware address that denotes the host. This means that the identification of your hardware will be attached to every communication across the Internet, an easy-to-follow trail. This has raised some privacy concerns, and a mechanism that automatically generates a unique random bitmap for this part of the address has been developed to solve the problem. This is up to the network administrator. Which solution will be used in the local network depends on the software. The random value needs to be unique on the local network, something that is checked automatically before the host communicates on the network. There are several address classes for identifying each node in IPv6, like link local address, site local address, and global address. Adding an FE80 prefix to the address makes this a link local address. A link local address works on the local area network, LAN. It cannot be used outside because it lacks all network identification. It's basically an address consisting of the host's hardware address. A site local address includes a subnetwork identification within the corporate network or the intranet, but cannot be used on the Internet since it lacks a global identifier. The subnet ID is assigned by the corporate network administrators. An aggregatable global address includes a global network identifier and is used globally on the Internet. The global network identifier is assigned to the company by the Internet service provider. This field is divided into several subfields, with parts belonging to the ISP's backbone provider. The address plan forms a hierarchy, where large backbone providers divide their addresses between ISPs who divide their part into addresses to customer networks. The host gets all the network identifiers automatically from the router and thus configures itself. It uses the link local address, which in most cases is the hardware address, to send a request for the rest of the address to the router. After getting a reply, the host is ready to communicate with other networks. A computer attached to an IPv4 network needs a basic configuration to be able to communicate with other hosts. A basic configuration starts with an IP number. To be able to send data to another host, that host also needs an IP address. All data is sent to IP addresses, not host names. When sending data, the host needs to find out if the recipient is connected to the same IP network. This is done by looking at the subnet mask of the network and the recipient's IP number. Subnet masks are usually configured in a way that looks like IP numbers, with 4 groups of numbers divided by 3 dots. In the newer implementations, you configure a mask by saying how many bits are used for the network ID. In the network in our example, a /24 mask is used, which means that the host's IP address consists of 24 bits for the network ID and 8 bits for the host ID. By examining the IP number of host B, we can see that its network address is 192.168.40. This means that host B is connected to the same network as host A. This is a minimal IP configuration, which gives the host local connectivity on the IP network, but not any ability to communicate with other network. Let us add another network. Instead of one local network, we have 2 networks connected with a router. If we want to send data from host A with IP number 192.168.40.3 to host C with IP number 192.168.31.32, the data must be forwarded through a router. The router that connects the 2 networks needs IP configurations for both interfaces. Furthermore, all hosts need to know the address of the router on their local network. Note that hosts A and C have different addresses to the same router, since they are connected on opposite sides of the router. Now, host A uses the network mask to check the network numbers for itself and the recipient. Since host C is connected to another network, the network IDs do not match. Host A has to rely on the router to find host C and send all data to the router. The router forwards the communication on to the next network, where it reaches the destination, host C. To enter the IP network configuration manually on each host takes a lot of time. Also, it doesn't make changes very easy if every change to the network configuration has to be manually entered into every host. To simplify administration of the host's IPv4, host configurations can be automatically assigned by a DHCP server. The DHCP stands for Dynamic Host Configuration Protocol. A DHCP server configures hosts for communication on the network. The term host in this case means an IP host and not the computer in general. Remember that DHCP does not configure the operating system nor the applications. When the PCs start up, they automatically connect to the DHCP server and get a host configuration. They are then a part of the IP network. Configurations can be permanently assigned or leased for a limited period. When the lease time expires, the host has to request for a new lease. DHCP can deliver more than the basic configuration. The server may also configure the printer addresses and other network services. For connecting a PC to the Internet over a telephone dial-up modem, a protocol called PPP is used. PPP stands for Point-to-Point Protocol. To use PPP, the PC user places the phone call and meets PPP client software. In Windows, this is called a dial-up adapter. The PC connects to a modem at the Internet Service Provider's site. This modem is attached to a Remote Access Server, RAS, which is a device with the PPP server software. The PC user has to authenticate it by sending user ID and password to the server. The server will normally respond with a configuration that the PC will use for this network connection. This function eliminates the need for DHCP on dial-up connections. In IPv6, DHCP is not needed to configure the host for IP connectivity. IPv6 provides each host with at least 3 different IP addresses: link local address, site local address, and global address, to be used in different situations. To begin with, the host has only a hardware address, the MAC address. Using this address, an IPv6 host creates the first address by itself, without any configuration. This address always starts with FE80 to signify that this is a link local address. It may be used between the hosts, which are connected to the same IP network subnet. This addressing method is similar to communicating with the Ethernet addresses, and cannot be used to communicate with the outside world. The host sends out a neighborhood solicitation to check if another host on the same link is already using this address. On Ethernet, this cannot happen, since all network adapters have a unique address. However, it may happen on other networks. If no one protests, the host is allowed to use the link local address for communication on the local subnet. Next, the host sends out a router solicitation on the network looking for a router. If there is one, it responds with a router advertisement. This message contains the subnet 1 identification, which is used to create a site local address. With this address, the host may communicate with other hosts within the corporation or campus. It cannot be used for external communication. The site local address begins with FEC0. The router advertisement may also contain a prefix for a global network address. Address is given to the network by the Internet Service Provider. With this prefix unique for the site and the site subnet ID, the host can create a global IPv6 address. This address may be used to communicate with any hosts on any network. As you can see, the IPv6 addresses are long and hard to remember. For users, we have a naming system that is easier to remember, a system with host and domain names. The next part of this lesson will explain this system. Each host connected to a TCP/IP network needs a unique IP address. Since IP addresses are not very user-friendly, applications can identify hosts with the aid of easy-to-remember host names. The mapping between host IP numbers and the host names is stored in the host table. In a small, standalone network, this table can be installed in all computers. Host names are enough to identify all hosts on a network, and it's easy to set up unique host names. But when organizations start to connect their networks together, or connect to the Internet, this method does not work any longer. Another way to separate hosts and create unique names must be used. The Domain Name System, DNS, solves this problem. Each organization is given a domain name, and this name is attached to the host name. Even if two organizations internally use the same host name, the full host names are different because the domain is unique. Two organizations cannot share a domain name. The Domain Name System basically works the same for IPv4 and IPv6. This part of the course will be based on IPv4, but it also applies to IPv6. As the network grows, host tables with IP addresses and names tend to become unmanageable. Since all communication between hosts uses IP addresses, but the users prefer to use host names, an external database with mapping between IP addresses and host names has to be employed. The DNS server resolves host names into IP addresses by querying the database. A host needs to know the IP address of the DNS server to ask it for translation of other host names. This is the part of the basic host configuration. If a company network is connected to the Internet, and users want to access web pages on the Internet using host names, a standalone local DNS server cannot provide them with the IP addresses. It is impossible, not only considering the size of the database, but also because the Internet is an ever-changing network, which means that the data in the database would not stay current for more than a very short period. In this case, a local DNS server takes another row, in which it is called a caching DNS server. It is configured to find the data by asking other DNS servers on the Internet. Every piece of data it finds is cached for a limited time. If another host within the network asks the same question, the local DNS server will use the cached answer instead of trying to find it all over again on the Internet. This lowers the burden on the Internet name servers and shortens the request time for local hosts. Domain names consist of two parts. The last part is a top-level domain, TLD. In this case, it is a .com. The part before this is the domain identifier. It is unique within the top-level domain. All domain names and host names are case insensitive. It doesn't matter if you use upper or lowercase letters. Domain names are used for a number of applications on the net. First, using the domain name, we create host names that almost all applications use. In this case, the host identification within the name is www. Web, FTP, and email servers all have host names. The domain is part of the full host name. The domain administrators can create subdomains within the domain. They have the same functionality as domains and can be used in the same way to create other addresses. In this case, ERA is added to the domain name to create a subdomain. The domain names are used in an email as part of the email address. The text after the @ sign has to be a registered domain or subdomain, retrievable in the domain name system. It is not recommended to use a host name in this part of the email address. The text before the @ sign does not have any connection with the domain system, but has to be recognized by the mail server registered to handle a domain. This is registered in the DNS database. Host names, including the domains, are a part of the web addresses. A web address is called Uniform Resource Identifier, URI. Without the prefix HTTP, a web address is only a host name. The domain system is hierarchical. At the top, a number of servers handle a limited database covering all top-level domains, TLDs, and the address of each DNS server that handles the domain data for the TLD DNS zone. These are called root servers and are spread around the world. The TLD servers handle domains within the TLD. In the TLD database, every registered domain is covered, and for each domain name, there are addresses to the servers that handle the domain. The organization managing the TLD is responsible for making sure that each domain is only registered once within the zone, so that each domain is unique. TLDs fall into two categories: country-level domains and generic TLDs. Country-level domains, like .se and .fr, are based on the ISO country code. Generic domains, like .net and .com, each have separate rules for usage, either open for all to register or limited, like .gov, which is reserved for the U.S. government. The domains are registered by individuals or organizations. An annual fee is paid for using the domain. If a domain contains subdomains, these are handled by the same DNS servers or separately, depending on the domain administration and the organizational setup to which the domain belongs. The DNS server is an application that manages a database with the DNS data divided into zones. Each zone handles one domain. It may also include subdomains. The subdomains may be a zone of their own, like the subdomain sub.mycompany.com in our example, or included in the same zone as the parent domain, like the domains in the zone that handles yourcompany.net. Each domain is handled by several servers to gain load balancing and secure the access. The DNS server that stores and controls data about a domain is called the master server for that zone. The servers that contain a copy of the zone data from the master are called slave servers for that zone. A DNS server may simultaneously be master and slave for different zones, depending on the zone configuration. For a client, it doesn't matter whether the reply is given by a master or a slave server. The reply is always the same. A zone contains several types of data. The administrative record contains information about master and slave servers for this zone, email address to the administrator of this zone, and some timers and version numbers that apply to the zone data, like expiry time for a cached data. Most of the data is stored in the host entries. There are two different host entries in the DNS database: a forward entry mapping host name to the IP number, and a reverse entry that maps the IP number to the host name. The mail server pointer tells the email servers where to deliver the mail address to this particular domain. For each domain, the administrator can register several mail servers that handle email and rank the mail importance. Mail is normally delivered to the primary mail server. When this server is not available, it is delivered to the next server and so on. A recent addition to the DNS system is the ability to store public security keys that are used in various applications and by the DNS system itself. Let us analyze what happens during a domain query. We assume that it is the morning of a working day and the network has not been used since all the devices were turned on. A user at the host Pluto wants to access the Ericsson website. He enters a web address, www.ericsson.com, in the browser. The user's PC asks the local DNS server for translation of the host name into an IP address. Since the web address, www.ericsson.com, is unknown to the local DNS server, it starts the quest by asking the root name server for the address to a server handling the .com TLD. This server is somewhere on the Internet. The root server replies by referring to a DNS server responsible for the .com top-level domain. The local DNS queries the .com DNS server for Ericsson.com. The name server replies with the address of the Ericsson.com name servers. The local DNS server now queries the Ericsson.com DNS server for the address of the www.ericsson.com host. The server replies with the current IP number for the web server. The local DNS now has the answer for the host Pluto and replies. The web browser contacts the web server at this IP number and retrieves the web page. During the process, all replies are cached in the local caching DNS server. The next time any host on the local network contacts www.ericsson.com, the reply is retrieved from the local caching DNS server. After a time specified by the Ericsson.com DNS server, the www.ericsson.com address is not trusted anymore and is deleted from the cache. A local caching DNS server also measures the time it takes to get replies from various DNS servers and uses the fastest available way to query. The router is a node that connects two or more IP networks. To be able to communicate with other networks, a host needs to know what services the router provides and which networks are reachable through the router. This information is recorded in a roadmap called a routing table. Each entry in this roadmap is a route. The routing principles are the same for both versions of IP, version 4 and version 6. In this lesson, the examples will use IPv4. All traffic from the host Pluto, destined to other networks, has to pass router A. Since there is no other way from the network .41, Pluto's roadmap is simple, with only one entry, the default route. A default route is the way out of the network, if no other routing entry is applicable. Router A has two network interfaces and a routing table with two entries. All traffic to network 41 is routed to the interface connected to that network, and all traffic to the hosts on network 44 to the other interface. The traffic to other addresses is returned to the sender with an error message. To connect the .44 network to the Internet, we attach a second router. This router has a routing table entry for the .44 network and a default route entry for the router on the Internet Service Provider's network. The host Mars that is connected to the .44 network and configured to use router B can now surf the Internet thanks to the router's routing table. The host Pluto cannot access the Internet, since router A is not aware of the Internet connection through router B. Clearly, router A needs to be reconfigured. In this example, the host Mars wants to communicate directly with the host Pluto. Mars uses router B as the default router. Router B has added router A to the routing table and can direct traffic to the network connected to router A. Mars starts the communication by sending the packets to Pluto through the default router B, since Pluto is not connected to the same network as Mars. Since router B recognizes that Mars can reach router A directly, it sends Mars a message to redirect traffic directly to router A. Mars adds this entry to its internal routing table as a dynamic entry. Next time Mars sends packets to Pluto, it sends packets directly to router A instead of via router B. On the Internet and in large corporate networks, routers inform each other about local network connections with special protocols called the routing protocols. This way, network managers do not need to add pre-configured static entries to every router. Instead, the routers build dynamic routing tables by listening to the information from other routers. Each dynamic entry has a limited lifetime so that the routers and the hosts do not save information as static information forever. Routers are divided into several categories depending on properties such as the number of interfaces and the understanding of various LAN, MAN, and WAN link technologies and supported protocols. To connect a small network to the Internet, only a simple Internet access router with one internal and one external interface is needed. This Internet access router connects to a larger access router on the ISP's internal network. The access router, with many interfaces, must be able to handle different access technologies like ISDN, ADSL, and phone lines with modems for leased lines and dial-up. It aggregates all traffic from customers onto the core router. The core routers must understand a number of network protocols to be able to build a routing table that covers the entire Internet. These core routers usually have several interfaces connected to various network providers. Connecting internal networks to the Internet raises the issue of security. We need to limit the access from the outside network to internal resources like intranet servers, printers, and legacy systems. The device that handles and controls traffic between networks from the security point of view is called a firewall. A firewall is basically a router with a lot of control functions. Firewalls implement a set of rules that all traffic is checked against. There are different rules for incoming and outgoing traffic. Firewall rules depend on the sender, the destination, and the protocol used. In some cases, they also depend on the content of the data. For example, firewalls may check for virus in web pages and email attachments. The security rules that the firewall enforces are made by the personal group that manages network security. This is done manually, and it's an ongoing process with regular updates. Some outgoing traffic is allowed. It depends on the security policy of the company. The non-authorized incoming traffic to the internal network is prohibited due to the risk of attacks on internal hosts. A problem arises if incoming traffic is not allowed. Some servers need to be public, like the web server and the email server of the company. But we cannot open holes in the firewalls that can be used for attacks. Also, the web server and the email server need protection from the firewall, even if they are public. The solution is to create a new network called DMZ network and connect it on a third interface to the firewall. DMZ stands for Demilitarized Zone. The public servers are connected to this network. Now, we have three different traffic flows: traffic to the Internet, traffic from the Internet to the internal network, and traffic from the Internet to the DMZ network. The firewall can have different rules for the different traffic flows and can separate the internal network from the DMZ and the Internet, making the public servers accessible from outside without putting the internal servers in danger.